Welcome to Applications of Maximisation and Minimisation. Some practical examples that we could see this used in life. So companies will use it to maximise their packing boxes, to come up with a maximum volume using a rectangular piece of cardboard. Flights, you try to minimise the amount of fuel that they use, or even when you're driving your car, there's set speed to go to minimise your fuel. You might minimise the amount of metal that's used in a can of soft drink, soda, etc., tin veggies, and that can then lead to maximum profits for a business. So the first thing you need to do when you're approaching a maximum or minimum question is to look for the detail that actually tells you that that's what the question is. So you're looking for the word maximise, minimise, in the question itself, whether it be an area, a volume, fuel. Diagrams sometimes can help. You need to write out the formula for what is to be maximised or minimised. And then you rearrange or use substitution to form an equation that only has two volumes, two variables. The first variable is what you're trying to maximise or minimise, and the second variable is the pronoun rule that you're working in. And then you find the maximum or minimum, making sure that you prove either using the y dash table or the y double dash concavity. So we're going to have a look at an example. So we've got a rectangular box that's going to be made. We're going to cut square corners from a piece of cardboard that's 8 metres by 8 metres. And then what you're going to do is you're going to fold those sides up, and we'll end up with an open rectangular box. Here we're trying to find the maximum volume. So I've just emphasised that a little bit more here. So it's a rectangular box, so that's the formula we're going to be using, and we're going to maximise the volume. So we're going to come up with the formula for the volume. Then we're going to show that it's a maximum, or show what is the maximum length of square that we're going to be able to cut out. So here's a nice diagram to help us. So you can see we start with our 8 metre piece of cardboard. We cut out squares on each side, let's call them lengths of x, giving that middle section 8 minus 2x, because we're minusing 2x from each side. When we fold it up, our base is 8 minus 2x, and it's a square, and the length of our, or the height of our box is x. So now let's maximise our volume. So we know that the volume for the volume of a prism is area times height. So the area of that base was 8 minus 2x times 8 minus 2x with a height of x. So if we expand that bracket and then multiply by the x on the outside, we get the volume formula is 4x cubed minus 32x squared plus 64x. Notice that we have two variables. The volume's a variable because that's what we're trying to maximise, and the x is the other variable because that's the unit we're working in, lengths of x. So we know from our curve sketching, the first step is to find the stationary points. And that occurs when the first derivative is equal to 0. So you differentiate, let it equal to 0, take out a common factor of 4, factorise into two brackets 3x minus 4 and x minus 4, giving you your stationary points are x equals 4 and 4/3. So then we substituted, I'm going to use the first derivative table. So we substitute the values into that. So 4/3 and 4 were our stationary points. So there, v dash is 0. And then we pick points either side. And we can see that we get positive, 0, negative, 0, positive. And that means that we end up with a maximum at 4/3 and a minimum at 4. And what we're after was the maximum volume. So we've proven that the maximum occurs when x is 4 on 3, giving us a maximum volume of approximately 38 metres cubed. Thank you.